Myself, Lieutenant Dr. Arul Arasu, on behalf of recent trends on loss of the to call upon our head of the department. Welcome address, ma'am, please.
All present here. Respected principal, guest Dr. Ponmurugan, my dear students. Webinar. Thermodynamics is a core part of science. Ago, with the invention of an engine by some as an old thermodynamic perspectives, thermodynamic are at the forefront of scientific and technological for thermodynamics is its large scales, which range from and to stars and galaxies. Thermodynamics has states with non-extensive practically on Earth has become one of the principal issues in on understanding the laws of thermodynamics. It's a privilege that we explain the laws of thermodynamics, and I person and exchange opinion about the in a rapidly changing world. Thank you one and all for
Thank you, ma'am. Thank you so much for the welcome address. Now, I would like to call up Santosh Babu, sir. Yeah, sir, please. Sir, your voice is not.
Good morning, one and all present. Head of the Department of Physics, and our Professor Dr. M is working in our college on behalf of the management, sir. Welcome you, sir. Members of the physics and the students this today's program session, thermodynamics. Sir. Basic science plays an important role, especially the physics plays a very in conservation of energy. Conservation of energy, the thermodynamics output for the a lot of awareness program to save the energy, population growth and other things. Have to work hard in the innovation. I know that the thermodynamics, as a lay person, as a computer science person, energy conservation, any other type of energy. Wherever you go, the whole body, we could not. We have to conserve our energy whenever the next is pleased. So this is the prime by the universe. So keeping in this mind, physics is organizing this today's program. So you know that a lot of trends, energy, okay, solar energy, then water you can generate an energy. All these things have. There is a lot of recent development. So that is to be updated to the student. So keeping in this mind, I think this again I congratulate the department for right topic and the right person for delivering it. Thank you much for giving this opportunity. Thank you.
For the thought-provoking and scintillating presidential. Now it's an opportunity for me to introduce the speaker. Completed his post-graduation from, and after which he has cleared his SLET exam and he has cleared his JRF NET exam. Igkar Kalpakam at the University of Reading, United Kingdom. Mathematical Sciences, Tamil Nadu. Project on free energy studies, neural protein adhesion. Sir, the amount and his core areas of computational and theory, interdisciplinary condensed matter physics, which in polymer melts, feedback systems and Q statistics. So these, and apart from that, he has also won the award, that is the Fast Track Young Scientist Fellowship. Thank you, sir, for the webinar. And continue with the sessions.
Thank you, sir. Thank you for Reversible, sir. Sir? No?
Yes, sir, please.
Yes.
First, I'll cut the camera. Sir, can you see this?
No, sir. Like,
Suppose if any interrupts. Today I'm giving talk on the recent views on laws of thermodynamics because it to be first, second, and third year up. So because of that, I choose this topic. I present a talk like this. Prepare the slide. So you can, I will interact with you. I will ask the questions. You can answer. I will finish within that time. So I'm as introduced by Dr. Physics, Polar Basic and Applied Sciences, Central University. Okay. Some views on laws of thermodynamics. Talk is like that. So what my introductions. So introductions and another. First, I will give elementary introduction of the thermodynamics and the intermediate introduction of the thermodynamics. Only for introductions. The various level of right. Okay. So I'm telling about the all are the same. Okay. This is the study of energy transfer, form of heat and work. So the question is, I'm going to give it some of the things are you heat and work. Then naturally the question is, what is macroscopic system? This is a constituents. A macroscopic system Microscopic concept. Microscopic concept. This question will ask. Example is like gas molecules in a container. Macroscopic system, but entire system gas molecules in the container. Some macroscopic systems. Okay. This picture here. So okay. So this is a cup. Okay, heated in here some. This is the thing. So water is system, that is water. Tell me how many molecules water only for students. How many? Any ideas? Particularly for first, second year. Give me the answer. I'll give some 2 seconds.
Yeah, students, any one of you, please. So Akash Narayanan told it's Avogadro number.
Ah, okay, good, very good. Means it's not. I am taking only physics, chemistry. Now the trend is now we are. Other you should only learn physics. So this today's world is interdisciplinary. I am not saying interdisciplinary today. Of every topic, and you focus on one part. Okay, good. Very good. This is my meaning of macroscopic system. Heat. So heat. So I'm using the simple heat means that represent by symbol Q and work to energy transfer for a given thermodynamic reaction. For a given thermodynamic system, equal to energy transfer. Work in the system. That is why I'm saying this is equal to energy transfer. That in the system, you cannot say how much. You cannot say that how much energy is transferred between you and in terms of heat and work. Heat and work. This is important. Right. Then next is coloring word. Right? Each coloring word a jargon. So what is the meaning of that? I think you may know, some of them may know. But I'm giving one second. I'll start this. What is that? So thermodynamic process. What is the state of the systems? Then immediately the question is, what is their state variables, such as pressure, etc. Like these other state variables, change in the state of the systems. Variables can be variables. It depends on from going upon. Suppose some we are pressure, initial pressure, and a particular volume, and this pressure is final pressure volume. This is the mind. Also, extensive or intensive. So so this is example. Extensive and intensive nature. So which one is extensive? Which one is intensive? Can anyone?
Yes, students, you can type it.
I'm not able to see the chat box, so you can just tell me whatever.
Yeah, I will like.
It's fine.
Example for extensive color.
Yeah, Pradyumna.
It is not. I'm saying pressure and volume. It is. Please tell me which one is extensive, which one is intensive. So I want to know whether you really know what.
And volume is extensive, sir.
So because the reason is, suppose we take a container, a volume V, pressure P1 and volume P1, one container. Take pressure P2 and volume. If you combine these two containers together, what is the volume we expect? The P2. That is additive nature. Whenever there is a say extensive, this two system, pressure is not, so that is an intensive variable. So if something is not in additive nature, that is pressure. Okay, this variable shall be extensive on it. The intensive variable and volume is another. The variables can be differentiated to x. Right. Good. Then I said are very because it depends on endpoints. And work is I said it and work is the energy variables are path variables. It means what the path stays. So how it go from one particular instance, suppose I'm this initial point, then work are different. Suppose I'm look at my mouse, okay, it different ways. So depending upon the path I'm going, state, heat and works are different. So that is why different things. So okay, path variables and okay, right. Now the system, I said the macroscopic can generally be classified into three types. General case. One is the isolated systems. Another one is a closed system, and final closed and third system is it is complete. That means environment. Suppose we have some system from the surrounding environment, then this is. It means the closed system is one we can be extend. That is not such a kind of exchanges happens in the isolated system. Exchange with the system. An exchange of energy, number of particles. Here the exchange of energy and the matter of the surroundings. Closed systems. Examples. Any 1 minute. Very good. Flask size. The hot water inside a flask. It is completely isolated and there is no exchange of energy. There is no exchange of energy in the system. Normally, if you open the flask, not a closed system or open system. Suppose you open the flask. Completely closed, so it means isolated. Suppose you open. Any ideas? Okay, you go and ask your teachers, physics teachers. Let us open. It is a complete isolated. Suppose then what will happen to the flask and then flask, then it is a closed. No. But open system can exchange energy and matter. Next I'm going to that process I said, no, the process thermodynamic into an equilibrium and non-equilibrium process. In the elementary things. Okay. The process, a thermodynamic process classified into an equilibrium. Immediately then the question is what is law of thermodynamics? Right? The formulation of law are entirely based on whatever you learned in here from the BSc level, all are equilibrium process. All the laws of them are equilibrium process. Okay. That's what is equilibrium? a conditions in which all influences are cancelled by the system. Okay, this is the meaning of equilibrium. Equilibrium process means that what are the influences causing the system changes are the system. So that is, we can say that there is no net particle. Then in general, in terms of scientific life, we can say that there is net particle. So if what is meaning I'm saying that, let us take some examples. A cup, I'm eating the cup water in here. Heat is continuously supplied from the flask. See, look at this bubble. Can anyone tell me this is equilibrium or non? Anyone? Let's come to this one. You take some system here. It is initially, this is the closest one. Okay, here top system is, you can discuss some. Let us take it the systems. Okay, now particles, most of the particles are initially. There is a whole system. So what will happen is, initially it is here. Okay, and after times from here it goes on here with inside this holes. This is the initial state. So once it's come to this state, okay, from here, but when you see an open eyes, we cannot change any change. Expect any changes on that. So it means the net changes is 0. So this kind of, so this is the thing. System initially the net transfer of particles from here outside also is going out. Once the time goes on, as time increases, as time goes, state in such a state that there is no movement of particles from outside. There is no heat also not changing within the outside the system. So it so that comment fixed number. It's a movement of the particle. The process is called, when our system comes to this state, now something in the system. When you come completely a non-equilibrium process, because we are energy passing through from the outside to transfer. But here there is a net energy transfer. Particle transfer 0. Next discussion class. Okay, fine. So now we were talking about the process can be either, no, you may know most of the times, no, it's irreversible process and reversible process. A reversible process is one, is same in forward and reverse. We grow from here to there. Suppose I'm start from here, start here. Slowly on like that. Now I'm coming to same path. Same path I'm coming like that. Then also reversible process, other thing is if it is not like, then it's irreversible. Input of external energy is like, okay? The input of initial state. For irreversible process, it is not that, but irreversible process, then you have to supply some states. So this is irreversible process. Then does not say means in its forward direction. That is an important point in irreversible process. The process is same, but here it is not the case. Same as in. So I send the change of state variables, right? So depending upon the process can further class the isobaric process. This isobaric process means constant process. That is, the process takes place. One state variable is constant. The other, if the compressor is constant, we call it one intensive variable and one extensive variable. Variable constant or intensive variable. So then depending upon we can differentiate process. Tell me any other process for an isobaric. Which one is constant?
Heat.
His enemy is E process. Constant. So heat is what variable? It's a state variable. Path variable. So it is what? So it not only the fixed state variable, you can also for path variable you can take the path variable adiabatic process. So adiabatic. Iso. Isothermal process.
Temperature.
Where is this the intensive variable or extensive variable? So you said B intensive. Okay. So temperature is the intensive variable. So for isothermal intensive variable, that is a constant. For of it is constant. There is no flow into the system, out of the system. It must use the law of thermodynamics. I said equal of thermodynamics already based on equilibrium process. Now I come to the laws of thermodynamics. Okay. Level. Initially I started any. This is now come to the intermediate level. So because this is the one we need. It is global because these are the things you have to give this whether we know elementary introduction of this thermodynamics. Now I'm so here human elementary you can say that. No, this is intermediate. Why I am selling? Okay. So, law because zeroth law. So what is actually zeroth law? The zeroth law says that this is that is temperature. Consider thermodynamics. You know anything about transitivity? Anybody know about transitivity? In maths, you transitivity property. So that is why I said if you study little bit chemistry, you should know good in mathematics, good in biology, and also computers. Interdisciplinary, not one. Okay, so this is a mathematics very good play, very close. Not only for any sense. Okay, so if somebody don't A is equal to B. Okay, some A is equal to B. Mathematics things. Okay. Someone is saying B is equal to C. I'm equal to B. I'm taking another in the message when observe from this. See, what is the message in there? Yes, B is equal to C. This is property in mathematics. The same transitivity got applied in. You cannot know this kind of thing. They don't say what is zero that means. They say equally with the system C. Then A is equal. actually meaning this transitivity property. Okay, that so it means A and B is equilibrium. B and C are separately equal with A and C are equal with each other. So in the mathematical transform name that equilibrium that C are equilibrium or not. Equal. The third body is equilibrium and B and C is of B here. System C are equilibrium or not. The B is a thermometer. Say that whether system some true system. I said there is an answer via thermometer. So we can get good. Okay. Right. So what is first law? So as the SAR principles has said that conservation of energy. Energy neither from one extent to another form. So in this case, the temperature is here. For law of thermodynamics, we can do one variable. Come temperature T. Now come to the first law. Energy is conserved. Another variable, that is state variable. The state variable. Then energy. Here I must change delta and use to Q plus W. Keep in mind. And W the energy. If adding these two things, get a change in variable table. Keep this by the same tables. Okay. Tables Q plus W. One form of Q, so things conserved Q plus W changing in the system. Okay. Now we come to the second conservation of entropy. Activity property. The second law in terms of the now energy is conserved. If you come to the second law, entropy is not conserved. Entropy can never or always increases. This the important point is variable temperature T, that is in we get another variable that second law, there is a one more variable that entropy that is defined as delta S. Delta is Q by G, that is U is a heat. Of intensity with T, we get a one quantity change in entropy. Okay, this is generally we call it gaseous init. Usually, what is second law is the second law talk of irreversibility. So it talks about how this important second law. Variable not and first law whether the energy is non-constant entropy in concept of macroscopic irreversible. So third law entropy towards absolute. This is third law. How entropy now the second law from how entropy. So this is a quantum conscience thing. The third law is based. For interest to go on it, thermodynamics. I already told a formula is not equilibrium process. I'm still thermodynamics are entirely based on equilibrium process. Is it valid? So this is the question. In the thermodynamic system, whatever in the first year, second year, whatever year you studied RNE, but in the thermodynamic system. Down and all the laws are formulated. Why that is the reason? Is it valid for a non-equilibrium? Okay. What is the meaning of non-equilibrium? Particle. But in the case of equilibrium, that is not it. So that is why I say in this three laws, four laws. What about this non-equilibrium? Energy transfer on it. Fundamental things. So zeroth law I'm saying this. Let us come to one second. Closed equilibrium system. Variable called temperature. You want that? This is for a zeroth law and for a closed system. Allows us to assign an. So temperature is rigorously defined only at equilibrium. It is formulated only for equilibrium case. So temperature is rigorously. Then again I ask the question. This is the next. It's valid for equilibrium process. Is it valid for non-equilibrium process? Is that there is no temperature beyond it? Is there intuitions? Anybody? Law is from temperature is formulated for zeroth law for equilibrium. Now I'm coming. I'm saying reason because equilibrium in beyond temperature, beyond equilibrium, is going on that. That is why I put it in. Okay, next. Systems. I am saying it means energy can transfer and particle are. That is why it's an open system. But to assign another intensive thermodynamic variable called. So keep it that in the case of closed system, this law allows zeroth law. When you come to the open system, this law allows to assign potential. You know, right? Okay. So amount remove or insert, how much energy required to insert or okay, right. Yes, systems. They always focus on closed system. It's focused on open systems because they are in chemical reaction. That is why most of things is always mostly focused on chemical processes. How much concentration two systems together, how it interact with the land. This is physical equilibrium. Okay, right. So just to go on it and then again, there is no temperature below chemical potential. So then there is no temperature for equilibrium. Beyond equilibrium, so this is the question. So these are the reasons. So that is why I'm saying this is 10 years before. That is why I put intermediate. Okay, still this is going on. If it equalizes the set of intensive variables. If the variable when two systems are kept and allowed to the number of particles, etc. This is zero intensive variables contact and allowed to exchange the corresponding particle. That is why I said no, suppose if we take one system, another system, whether some temperature is reached, so it keeping the, that is why the corresponding extensive extra. Okay, this is the thing. So equal variables, that is temperatures. You make it up, and also it has been also years is not such a big thing. Okay, recently I think you may not know that is gas. Leave it about some gas models. Open, that is open system. In the non-equilibrium steady state region, that even for a non-equilibrium systems, okay, zeroth law. So first one is they observe these things. Some scientists from that, they observe that from that some models, some gas models, they find that for that open system, they find that even for non-equilibrium steady state, they can satisfy the layer of it means the intensive temperature are also the chemical potential is also valid for what? Non-equilibrium system. It means zeroth law also valid for a non-equilibrium systems. This is the answer they got. To define it, open top. Say what also is there, and also what is the limit setup. Yeah, I'm saying in terms of a. So is that so that is a define it. That is open top. Still it. So zeroth law valid for a non-equilibrium system, temperatures. So still it is normal because still the debate is going on. So for a non-equilibrium system. Okay, right. Now coming to the first and second one. The first law step, I'm putting different statement over second law. The universe is a constant. Okay. The author is Jill Laban. This book is go and read it. This books. Okay, this is a book. That the energy of the universe is I mean different statement of second constant, and second law stating that the entropy of the conservation, I put in the conservation energy in different way. First law stating and second law stating that the entropy never decreases because the entropy is always increase. That is why I said. Third, when you come to the second law, entropy does not constant. So it is always and generally valid both for in zeroth law also now instance is valid for equilibrium cases and second law also. These are the things. If you want interest to go on, this is mat. This is some kind of reference. Okay, go mat, and this is a number of them. Those 11. Okay, still the and starting about. So what these two laws, first and second, and unequilibrium process, because it talk about energy of ever decreases. Now I'm coming to that does not prefer a direct sense. How the system evolves, it does not take for the evolution of the systems. Okay, so what I was saying, energy is how the system changing from one particular direction. That's why I say. When you come to the second law of process, I put in for equilibrium reversible process, then less is equal to Q by T time. For equilibrium reverse, change in entropy is equal to Q divided by T. Reversible process, then less is greater than Q by T. This is the thing. So here equality is second law. For equilibrium process, reversible process then less is greater than Q by T. Suppose we take a egg. Okay. Right, is egg. Okay. Now broken. Now tell me, see what is that? Initially it is that, and now it's broken. It will be increases or decreases in this case. Entropy increases. Okay, so you're saying entropy increases. I'm taking another case. In this case, what about this? Suppose what about here the entropy is here and the entropy is here. That is the entropy. What about this? What about the entropy of this? It's less in this case. Compare to this big. The same some kind of broken like that.
It increases even.
Okay. can you tell me name of your name? Your name? It's more. Okay, let us come to another picture. Like that. What about the entropy? Even
Maybe
more?
even, yes, sir.
It will be even more. Okay. So saying this here entropy is like that. It is more like this. Suppose entropy is even increases. What does mean increase and how we quantify it? Any change in entropy here changes in saying entropy increases. How the entropy increases? So in this we go to statistical mechanics. Let's say that entropy here in this case entropy is less. What I cannot go on like that, so I will stop. Okay, if I go on read like the how entropy in this case, another case, right? In this egg is broken. In this case, what about entropy? In this case, okay, I also don't know.
I think it would be an example of irreversible problem. Since in the other case, take some effort to bring it back to the same, it would not be possible. So the entropy.
Here it is greater compared to this. No, it is not like that. Okay. Being back to original egg, broken it can bring
to
out
take some
the
effort, amount of work needed would be more. Difficult, but it might be possible, but
it may be possible but difficult. So this is it means you cannot do it. And make it like this. So it's not practically it is not possible. If you're an experimentalist, I can say that. Some little bit like that. Yeah. Okay. Just try. Because this is a simple example. Some interest. Second half Thursday. Okay. Right. Just check it. Right. Now I'm saying 1 second. Okay. So for equilibrium reversible process del S is great. Okay. So how to quantify process del S is greater than Q by T. Okay. Reversible process del S is greater than Q by T. Okay. For that, so now look at that. I'm coming. I'm giving in only in total. Keep in mind, I say in the first sections over and intermediate final stage of this talk. Okay, advancement. So that is why there is a name here. These are the reasons, right? So what is entropy? Equal to del S minus Q by T. This is entropy. Entropy for it. Okay, when you take this sigma called the term, this called means the same thing. Del S is same as Q by T means sigma is 0. That is for reversible process in irreversible process. I'm introducing another quantity entropy produced depending on what entropy is more for less reversible entropy is less like. So this is for highly reversible. This is little bit reversible little bit compared to this, and it is more reversible compared to quantifying the cases. I use the term sig is del S minus Q by T. That is process. Those who are interested to learn more than thermodynamics, introduction of thermodynamics of irreversible. This is very we can get some perspective of irreversible process. That is other trend is going on for scientific trend going on. Right. Okay. And law. Okay. So non-equal process is irreversible. Okay. Keep in mind non-equal process. Second law. Then how to define enterprise? I said sigma, no? How to define general? Discuss only for temperature. I said different for case. In case, how can define enterprise? In that is equal to sum of I, J I X I. This is for different variable. That J known as the thermodynamic. They are conjugate thermodynamic forces. I said J is a flux. Example. Here, what is flux? T is a thermodynamic force. Simple example. That is equal to sum of I, J, X, I. There are so many thermodynamic fluxes, forces are there. One simple example, thermodynamic flux, heat. Another one is thermodynamic. Similarly, you could go to other things. Example. In general, I'm saying that I think this is called general entropy. Just go and read some books. If we know statistical mechanics, go and read. Otherwise, leave it. So there is no specific what should be flux and forces. A specific rule to identify which one is for. But simple, I'm saying simple as the previous that Q is here. Temperature 1 by T, temperature thermodynamic forces. Some example of force. Heat vectors, viscous are dissipative field, strain rate, tensor, that is 10th. I think these are some advanced levels, so don't forget about it. If you do, okay, right. So I'm saying that now I'm putting the second law. Second law, a macroscopic reversibility, that's sigma 0. Whenever sigma is equal to 0, greater than 0, it is a reversible process. When you come to the microscopic level, so I said no, construct a microscopic quantity. When you come to the microscopic small level, so we can take in sigma can be negative. In general, sigma is always microscopic. When you go to the microscopic quantity, means a violation of second law can be observed. Keep in mind, the second law is system. It is always great. Microscope, that is as very small systems. To second law can be a violation of the thermodynamic system. This is an advanced topic of this thermodynamics. So entropy can be negative. So the behavior of that, the behavior of the microscopic constant is different. If you go to single particle, how single particle small, some 2 or 3 is different. When you come to collectively all the particle behavior of the microscopic constants of the system in macroscopic behavior emerges collectively. Advanced thermodynamics. If you go to individual program is going on them. Suppose the individual behave differently. Suppose a collective persons, number of persons are there. Other persons moving like that. So that is why the peoples are behave differently. When you go to individually, that behavior is different. Here also, the bigger of the macroscopic constant of the system macroscopic behavior. So these are the recent trend on small, remember that small thermodynamic system. Some say that protein. Biology. Keep in mind, I said initially, that is one example. No, so okay. Next, I'm saying sensitivity mathematics. Now I'm going to the small thermodynamic system. What is protein? Single protein has in how it behaves. Microscopic systems. Okay, in this case, this value second law is violated. Now, physics is valid for biology, also valid for biology. Initially, I start with the physical system, biology system. When I come to the biology system, a single second law is violated. The bonds to use. Now, in this case, how to next question is about how to identify a violation of second. Think connect. Hello? Yes.
Sir, excuse me. Question on sir. There is one question in the chat. Sir, does that mean entropy will entropy
Increases at the microscope. That is why I'm saying entropy when you come to the microscopic level. That is what I'm mentioning. And whenever entropy negative means decreases. It can be negative. So that is how to quantify the second law violation. That is some relations that called. This is statistic. That if you are statistics, you know something on statistics, because I'm starting with students are from different. So I'm not talking about that. That is statistical algebra. Saying first year, you know where they come. Data fluctuation is highly. So that is what productions fluctuation. There are fluctuations that. So this when they say P of sigma is the entropy productions is P of sigma. Because see, I said the question asked no entropy that, so it means P of minus sigma. What are positive productions, positive entropy production, and the negative entropy production. This is equal to X. Somebody come on the relations. Because the entropy productions are consumption and the negative entropy production minus sigma. P of minus sigma is the second distributions. This is exponentially suppressed. The ratio of P of sigma to P of minus sigma is the tau is a time. Okay, some time that is time, long time period. Put all the things. This is some tau. When time increases, okay, exponential factor increases. So this P of no meaning is suppressed. Okay, the second level, this exponential increase in functions because we cannot observe negative entropy products. One can observe extreme. Remember that negative entropy product. Extreme entropy production and negative entropy production is probability of minus sigma is equal to exponential of that comes steady state fluctuation. That is another one. Relations. It means what is the standard equilibrium at inverse temperature beta. So in this, not necessarily equilibrium at initial state and final state. In equilibrium. When come to the final state. So in this case, so what is the relation is P of power beta sigma. Here look at that. That is a quantity beta. So that is beta is equal to 1 over t. Or go to some constant. That is going to put it here. E power beta sigma. System, in this case, system should be driven between the two arbitrary tau. Good. For case like that, for any kind of tau, system should be process. So this is transit state. This fluctuation is advanced topic in that what I make systems. Relations the work fluctuations. Okay, I think I don't go more on that. In terms of sigma entropy productions, that is one more thing. What P of minus W is equal to E power beta. Similar. And one more fluctuation is called proves detailed fluctuation. Then divided by P of minus W is equal to E power beta W. What this is W is below W is equal to is the change in free energy. I think you know what is change in free energy between the two equilibrium state of a given process. And by a charge, some persons call charges for a non-equilibrium process. Remember that for sigma is greater than 0. Within this, some concept e power minus beta. This beta, this is equal to e power minus beta of del R. the molecular process. Okay. This is the one concept that I will stop there. Okay. I'm putting the alternative of second law in terms of work. The first law is del S is greater than or equal to Q by T, and you STS. So change in free energy is for an isothermal process D greater than or equal to Q. Okay, you know, we can write second law in terms of work is W is greater than or equal to entropy, and also second law change in free energy. So I can write second law in Q or W is when the process is equilibrium, the work change in free energy or irreversible process, the alternative view of second law. When you come to the simple instead of taking this macroscopic W, this average W is greater than or equal to WD is called as this difference between these two products in del S minus Q minus. Similarly, I'm putting that in dissipative work is this W that is greater than or equal to 0. This is comes e power minus beta W average over all the microscopic cases equal to e power minus beta W. So this is second law. WD is a second law. So this is alternative in terms of I said everything in terms of entropy production. I already said same second law which violated in terms of the work done on the done or by the system. Okay, I think I'll stop now. Questions? Any questions?
Please, students, any questions to be asked? Murugan sir, beautiful presentation, sir.
Thank you, ma'am. I think if the students can understand, I don't know. There someone students are asking this thing. Let us say.
Sir, hello.
Yes.
Yes.
சார் எனக்கு நீங்கள் இந்த மைக்ரோஸ்கோப்பிக்காக இருந்ததுன்னா அந்த என்ட்ரோபி நெகட்டிவ் ஆகிறதுக்கு வாய்ப்பு இருக்கு, மேக்ரோஸ்கோப்பிக்கில் என்ட்ரோபி நெகட்டிவ் ஆக வாய்ப்பு இல்லை, அந்த இது சொன்னீங்கல்ல சார்?
ஆமாம்.
இப்போ இதில் மைக்ரோஸ்கோபிக் மேக்ரோஸ்கோப்பிக்கு ஒரு கிளியர் இது இருக்கா சார், பவுண்டரி? இதுக்கு மேலே போச்சுன்னா வேலிடு அந்த மாதிரி டிஸ்டிங்ஷன் கிளியராக இருக்கா?
அந்த மாதிரி டிஸ்டிங்ஷன்ஸ் கிடையாது. ஏன் சொல்றேன்னா இதை சொல்லி ஏன் அப்படி டிஸ்டன்ஸ் கிடையாதுன்னா, சப்போஸ் இப்போ எடுங்க ஒரு ஸ்டார் எடுத்துங்க, சப்போஸ் அவர் யூனிவர்ஸ் எடுத்துங்க. வாட் சிஸ்டம்? மேக்ரோஸ்கோபிக்கா மைக்ரோஸ்கோபிக்கா? Microscopic universe, entire universe. It's a macroscopic. Okay, and the universe is a macroscopic. When you go inside this universe consists of what?
Gases இருக்கு, நம்ம இருக்கோம், நிறைய particles, நிறைய microscopic systems.
அதெல்லாம் microscopic. What are microscopic? Stars are microscopic systems. Okay, and our solar system is a microscopic system. Okay, is it okay? Okay, so that's my system. So this is one kind of the macroscopic. The universe is a macroscopic system, and the solar system, stars are microscopic things. Okay, when you come to the solar systems, is it really a microscopic?
இல்ல. Okay, so relative limit.
Relative limits. What is that? When it collects, that is why I say what is. So I say in the first slide. No, I already told. Okay, so I'll come to that first slide. I told what is. That is why I'm saying that. Okay, just say I initially said macroscopic system is a collection of microscopic. That's all. That is the meaning of macroscopic system. How that what is microscopic? That is a relative things.
Okay.
Yes, so it means this is valid not only for small system, also large system, the universe levels. That is why thermodynamics is very interesting topic. That's why the choose topic is it can be valid for small system, it can be huge systems, thermodynamics, in terms of statistical mechanism. Is it clear?
Yes, sir.
Thanks.
Sir, so இந்த செகண்ட் லா வேல்யூஷன் வரும் proteins DNA அதெல்லாம் மட்டும் தான் இருக்கா, இல்ல in general it applies to all microscopic?
In general, it applies to any small thermodynamic systems. I'm giving simple example is a biological systems. If you're interested, go and read some books or some literature, you can get a better perspective of what are the systems. This is general in the second class highlight.
Okay, sir.
Sir, ஏதாவது books நான் suggest பண்ணுங்க sir, so that the students can read. Because இல்ல
நான்
நான்
இதுலயே
சொல்றேன். ஓகே.
புக் கொடுத்துருங்க. ஆனா வந்து என்னன்னா அது அவங்க எந்த அளவுக்கு அண்டர்ஸ்டாண்ட் பண்ணி அதுக்கு மாதிரி அந்த புக் போகணும். சோ அதனால ஃபர்ஸ்ட் பேசிக் இது கொஞ்சம் ஸ்ட்ராங்கா கத்துக்காமலே
ஓகே. நேத்து நான் பார்த்துட்டு வந்து நிறைய அந்த செகண்ட் லா ஆஃப் தெர்மோடைனமிக்ஸ் பத்தி that a lot of books that have come up இல்ல சார்.
ஆமா செக் பண்ணிருக்காங்க. எந்த நாலேஜ் ஸ்டூடண்ட்ஸ் இருக்காங்களோ அந்த நாலேஜ் பத்தி அவங்க வேற புக்ஸ் அவங்களே தேடிக்கலாம்.
ஓகே.
அதனால தான் நான் ஸ்பெசிஃபிக்கா நான் சொல்ல முடியல.
ஓகே 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 சார்.
இல்ல ஒரு ரீஃப் சொல்லுங்க மேடம். சிம்பிள் சிம்பிளா சொல்றேன். ரீஃப் புக் படிச்சா அதுல ஒரு பெர்ஸ்பெக்டிவ் வந்துரும்.
சரிங்க சார். ஓகே.
அந்த புக்லயும் அது இன்னும் பார்த்தா கொஞ்சம் பெர்ஸ்பெக்டிவ் கொஞ்சம் மாறி கொஞ்சம் வந்துரும். நான் லெவல்ல சொல்லிருக்கேன்.
ஓகே.
There is author. Go to that author entire book. They get a clear perspective and advanced level also.
Okay. Students, any questions? Yes.
Any other questions?
Sir, good morning, sir.
Yes, good morning.
Sir, thank you very much for the very inspiring lecture, sir. Sir, in doubt என்ன அப்படின்னா வந்து இந்த என்ட்ரோபியோட கன்சர்வேஷன்ன்றது குளோபல் கன்சர்வேஷன் தானே சார்? லோக்கல் சிஸ்டம்ஸ்ல என்ட்ரோபி கேன் டிக்ரீஸ் லைக் இஃப்
that is what I'm saying. Yes, locally entropy can decrease. Locally means what locally? Small systems.
Yes, sir. So the entropy is a global conservation.
Global conservation. That is what I'm saying. Yes. I'm saying the global level. When you go to the low level, entropy never also decreases. That is why I'm saying that. For a small thermodynamic system, okay, yeah, the entropy decreases. That is a violation of second law.
Okay, sir. Thank you, sir.
சார் இப்போ இந்த வயலேஷன் வரும் நான் ஈக்லிபிரியம் சிஸ்டம்ஸ் மட்டும் தான் இல்ல it applies to equilibrium systems also?
See, I already clearly mentioned for an equilibrium system, what is that change in entropy? Sigma entropy protection is 0. It does not valid for equilibrium system. I'm saying this is for non-equilibrium systems.
Okay, sir.
Sir, is the decrease in entropy, is it called as deacceleration in kekkararu?
Deacceleration, decrease in no, it is not related to deacceleration. That is why suppose if you have a knowledge of static mechanics, then I will come to the another way. So suppose we have some know about statistical mechanics. Entropy is what? Measure of disorder. Okay, so how orderness and disorderness is saying about this entropy? It is not come deacceleration, accelerations.
Okay. Ashwin, are you clarified? Our question in chat box la potirungar.
Okay. Is there any other still have a doubt after this?
Yes sir, yes ma'am. Anybody else has got any questions to ask? Sir கிட்ட நல்லா கேளுங்க, ஏன்னா நல்லா சூப்பரா சொல்றாரு. என்ன பண்ணுங்க sir?
Any questions?
Any questions?
See, that is why I say yes. Look at the here. Del S is equal to qubit. This is the second law. Del S is equal to qubit, or del S is greater than equal. That is why previous law is solved. Second law, thermodynamics definition of second law is this. See, I already okay. See, look at the second law. Non-continuous entropy. This is a thermodynamic in a definition. Del S is greater than equal to qubit. Thermodynamics point of view. When you come to the statistical mechanics point of view, this definition is not that. There is another definition. S is equal to k log omega. Boltzmann's law. That is different. When you come to this, there coming entropy is a measure of disorderness. Everything comes in terms of order disorderness for this case. So in this perspective, we are saying entropy is when the law of entropy, the second law violated. Thermodynamics second law violated. Any other doubt?
Anybody has got any questions to be asked?
No, ma'am, I don't think so. I think.
Okay. Sir.
Before that, I will say one more thing. See, don't think the students have a mentality that thermodynamics I learned in 10th, I learned in 12th. Why should I learn in plus one BSc first year, second year? Why should I learn in the MSc like that? Having but really, whatever they know, it is not that. Their understanding not that level. So when you come to the different level, you can have a different perspective of thermodynamics. That is, I want to keep these things right. Okay, for students, particularly for students. So go and read thermodynamics again. You will get a different perspective of reading the thermodynamics concept. That is my point of view. I'm saying this to students, particularly for students.
ஆக்சுவலா சார் நீங்க இன்னும் கொஞ்சம் ஆக்சுவலா ரிசர்ச் வந்து அது கூட பசங்களுக்கு நீங்க சொல்லலாம்.
நான் ஸ்லைடு இருக்கு மேடம், நான் சொல்லல.
ஓகே. இல்ல நீங்க வந்து பர்சனலி how was it you have grown up இல்ல? நீங்க சொன்னீங்கன்னா அந்த பசங்களுக்கு ஒரு இன்ஸ்பிரேஷனா இருக்கும். டெஃபினெட்லி whatever that you have achieved இல்ல, that is an inspiration to the students. Kindly students actually வந்து பொன்முருகன் சார் நீங்க தெரிஞ்சுக்கணும். he is a very hard worker. அதனால வந்து அவர் எப்படி கஷ்டப்பட்டு எல்லாமே பண்ணிட்டு கஷ்டப்பட்டு இல்ல, ஐ திங்க் he really liked physics, studying physics. புக்கும் கையுமா தான் நீங்க சாரை பார்க்கலாம். ஸோ ஆக்சுவலா நீங்க அது கூட கொஞ்சம் சொல்லலாம் சார்.
ஓகே மேடம்.
படிக்கணும்
சரி, என்ன சொல்ல வரேன் மேடம், நான் வந்து அது வந்து ஒரு ரிசர்ச் லெவல்ல வச்சிருக்கேன். பட் டைமிங் ஒரு பெர்ஸ்பெக்டிவ் 40 மினிட்ஸ்ல அவங்களுக்கு போய், அதாவது தேர்ட் இயர்ல இருந்து இருக்காங்க, நான் வந்து ரிசர்ச் லெவல் டாபிக் அதே மாதிரி கொடுத்துருவேன்.
இல்ல புரியுது சார். நான் சப்ஜெக்ட் நீங்க 2 வாரத்தை வந்து இந்த பசங்க வந்து படிக்கணும். So how should they study for physicsங்கறத 2 லைன் நீங்க சொன்னீங்கன்னு வெச்சீங்களேன், definitely அதுவும் நல்லா இருக்கும்னு சொல்ல வந்தேன், வேற ஒண்ணும் இல்ல.
அப்படினா நான் கொஞ்சம் செலக்ட் பண்ணேன், இன்னொரு டாக் கொடுக்கணும், இன்னொரு கொடுக்கிறேன். How to learn physics because நான் ஒரு டாக் கொடுத்திருக்கேன், நான் ஒரு இந்த காலேஜ்ல வந்து கொடுத்திருக்கேன், காவேரி காலேஜ் சொல்லி திருச்சில how to learn physics அப்படிங்கற ஒரு டாக் கொடுத்தேன்.
ஓகே. அப்ப நெக்ஸ்ட் அந்த மாதிரி ஒரு இது வெச்சுக்கலாமா சார்? ஏன்னா பசங்களுக்கு நிஜமாவே கொஞ்சம் ஒரு இது கிடைக்கும்ல சார், ஒரு டைரக்ஷன்.
அதுல ஒரு சின்ன என்ன தெரியுமா மேடம், அது வந்து நேர்ல பார்க்கணும் மேடம். பசங்க நேர்ல பார்த்து அவங்க எப்படி பிஹேவ் பண்றாங்க நான் வந்து அதுக்கு மாத்திடுவேன்.
புரியுது சார். ஒன் டு ஒன் பேசிஸ் இன்டராக்ட் பண்ணும்போது அது வேற மாதிரி இருக்கும்ல.
இல்ல அதுதான் இது வந்து இந்த டைம்ல வந்து இப்ப நான் நான் டாக் கொடுக்கும்போது அந்த மாதிரி பார்த்தா ஸ்டூடெண்ட்ஸ் பேஸ் ரியாக்ஷன் வந்து அவங்க என்ன புரிஞ்சிருக்கல நான் இது பண்ணிடுவேன், மாத்திடுவேன் அந்த டாக். இப்போ இதுல நான் ஒவ்வொரு ரியாக்ஷன்ஸ் எனக்கு தெரியல, அதனால இன்டராக்டிவா போனேன். இன்டராக்டிவா போகும்போது அவங்க என்ன புரியுதா என்ன பார்த்தா நிறைய வந்து ரொம்ப ஸ்லோ சைலன்ஸ், ஒரு 2 பசங்க தான் சொல்லிருக்காங்க கொஞ்சம் ஆன்சர்ஸ், மத்தது அந்த இது வரல.
இல்ல சார், பேசிக்கலி we only tell them சார், அடிக்கடி மைக்ல ஆன் பண்ண கூடாது எல்லாம் சொல்லி கொடுத்துருக்கோமா, அதனால வந்து கொஞ்சம் இப்படிதான் பண்ணுவாங்க. பட் ஆனா கேட்டிருப்பாங்க.
ஓகே மேடம். என்ன basically they should know, that is why there is no point in giving talk like that we spending our times and the students should get benefit from it.
That's very true sir. Because how much effort is being spent on preparing this PPT and how much planning is to be done in order to make this delivery, அது வந்து as teachers we understand, but ana probably on the student level la அது இன்னும் உங்களுக்கு அத்தனை புரியறதான்னு தெரியல.
இல்ல அது புரியாது மேடம். அது கொஞ்சம் அதுல ஸ்டூடண்ட்ஸ் ஒண்ணு சொல்றாது, என்ன அவங்க உட்கார்ந்து பார்த்துட்டே இருக்காங்க மேடம், பாத்தீங்கன்னா என்ன பண்ண முடியும், அதுவும் கஷ்டம். சோ ஒரு சின்ன எக்ஸாம் நீங்க சொன்னீங்க மேடம், நான் ரிசர்ச் லெவல் சொல்லும்போது ஐ டிட் சம்திங் ஆன் திஸ். தட் இஸ் புரோட்டீன் எடுத்து லுக் அட் இந்த பிகர் தெரியுதா மேடம் உங்களுக்கு, ஒரு பிக்சர் தெரியுது. சோ திஸ் ஒன் ரிசர்ச் லெவல் ஐ அம் சேயிங், see this is a protein. The protein name is called a F3 domain contact in one protein. Contact is a neural protein. Okay, for students I'm saying this is a neural protein, there is a single protein. So this is a macroscopic thing. Okay, look at it, is a macroscopic. This is a protein. Okay, so this is a folding one. Protein already folding la irukum, எப்பமே folding irukum. என்ன பண்றாங்க சார், எக்ஸ்பெரிமென்ட்ல சிமுலேஷன் சொல்லிட்டு செய்யறது என்ன பண்றாங்கன்னா அந்த protein என்ன பண்ணுவாங்க, எக்ஸ்டெண்ட் பண்றாங்க. So this is extend, it is here folding state, now extending them. So extending பண்ணும்போது எவ்வளவு நீங்க எக்ஸ்டெண்டிங் பண்ணா அதுக்கு ஏத்த மாதிரி இதோட மைக்ரோஸ்கோபிக் ஸ்ட்ரக்சர் சேஞ்ச் ஆகும். See, this is a small thermodynamic system. This protein is a small thermodynamic system. Why I'm saying thermodynamic system is it consists of many different configurations. This is a one configurations. இத நீங்க எக்ஸ்டெண்ட் பண்ணும்போது இது ஸ்மாலா இருக்கு, நிறைய சேஞ்ச் ஆகும். இது ஒரு கான்ஃபிகரேஷன், there is other configurations. So இன்னொரு ஸ்லைட்ஸ் பார்த்தா இதுக்கு பார்க்க தெரியல. இத பாருங்க, this is see look at that picture. Completely மோஸ்டா எக்ஸ்டெண்ட் ஆயிடுச்சு. இந்த பிக்சர்ல பாத்தீங்கன்னா இங்க புரோட்டீன் இங்க இருக்கு, கம்ப்ளீட் ஃபோல்டர் இருக்கு, அதை எக்ஸ்ட்ரா ஸ்ட்ரெச் பண்ணி ரொம்ப கம்ப்ளீட்டா எக்ஸ்டெண்ட் பண்ணி வந்திருக்கும். So these are the different microscopic constitutions. So இந்த மாதிரி கான்செப்ட்ல how much work needed to extend the protein அப்படிங்கற படிக்கிற ஸ்டடீஸ்ல தான் இந்த வந்து எவ்வளவு வந்து இந்த வயலேஷன் செகண்ட்ல எவ்வளவு வயலேட்ங்கறத ஜார்ஜன்ஸ் கை காட்ட போறாங்க. So அதான் இப்போ புரோட்டீன்ஸ் வந்து எப்படி ஸ்மாலா இருக்கு, எவ்வளவு எக்ஸ்டெண்ட், இந்த டிஃபரெண்ட் கான்ஃபிகரேஷன்ஸ் வந்து சொல்லி இந்த ஸ்டடீஸ் பண்ணி ஃபோர்சஸ் எவ்வளவு சேஞ்ச் ஆகுது, ஃபோர்ஸ் வெர்சஸ் எக்ஸ்டென்ஷன் படுது, எவ்வளவு வயலேஷன் அவுட் த செகண்ட் லாஸ் வயலேட்டட் அப்படிங்கிற ஸ்டடீஸ் ஆகுது. இந்த இதை நான் வந்து கொடுக்கல, ஏன்னா டைமிங் வந்து செட் ஆகுது. இதுக்கு 40 மினிட்ஸ் டைமிங்ல இது சொன்ன பசங்க புரியுமான்னு தெரியல, ரிசர்ச் லெவலில் வரும்போது அதை கொண்டு வரலாம். ஸோ அதனால சும்மா கொடுத்துருக்கேன். சப்போஸ் ஒரு பெர்ஸ்பெக்டிவ் கொடுக்காக இது இம்பார்ட்டன்ட், டைமிங் செட் ஆகுது அப்படியே நான் விட்டுட்டேன். நீங்க பாத்தீங்கன்னா இதுல வந்து அந்த இது தெரியும், இந்த ஸ்லைட்ஸ் பாத்தீங்கன்னா இந்த இது வேலிடேஷன் டெல்டா எஃப் வந்து ஈக்குவல் டு இருக்குமா இல்ல கிரேட்டர் லெஸ் ஈக்குவல் டு செகண்ட்ல வயலேஷன்ஸ் இருக்கா அப்படிங்கறத இந்த சிங்கிள் புரோட்டீன்ல நான் ஐடென்டிஃபை பண்ணேன். இது சிமுலேஷன்ல நான் எக்ஸ்பெரிமென்ட்ல பண்ணிருக்காங்க, வெளியில பண்ணிருக்காங்க. நாங்க பண்ணது வந்து சிமுலேஷன்ஸ் பண்ணிருக்கோம். கம்ப்யூட்டர் சிமுலேஷன்ஸ் வந்து நாங்க பண்ணது அந்த ஜாட்ஸ் ஈக்குவல் ஆகுது எவ்வளவு வெரிசன்ஸ். சோ இது ஒரு பெர்ஸ்பெக்டிவ் இந்த சைட காமிக்குது.
எஸ்.
Any other doubt? First one anything. Exactly.
Arul sir,
Yes, ma'am.
the students have not.
Yeah, I think there are no questions. So shall I close the session, ma'am?
Yeah, vote of thanks, please.
Yes, ma'am. So on behalf of
Meena Sharma wonders, sir. She has said, "Thank you, Dr. Ponmurugan, for enlightening us."
yeah,
She has
very true, very true.
Yes, sir.
Yeah, thank you, sir. Thank you so much for sharing your views on reason, trends, and laws of thermodynamics. Particularly the basic, intermediate, and advanced type concept was very much attractive. It has changed the views on thermodynamics. Whatever we have studied during our school days is different, and now we have to really redefine. I'm sure that a student will follow it up, and we will get back to you with the new topic, like how to learn physics. Definitely, sir, we will come back to you with this topic for another webinar. And once again, on behalf of Department of Physics at DG Vaishnav College, I would like to thank today's speaker, Dr. Ponmurugan sir, for spending his valuable time in delivering the webinar on the topic of reason, trends, and laws of thermodynamics. And I would like to thank our college secretary, Shri Ashok Kumar Mandraji, and our college principal, Captain Dr. S. Santosh Babu sir, and our beloved HOD ma'am, Dr. D. Shamna, and staff members of the Department of Physics, as well as the student coordinators for today's webinar, particularly Karthik, Kanishka, Sharma, and Pradyumna for their excellent coordination. And last but not the least, I would like to thank all the students and the participants who are present throughout the webinar. Thank you so much. Once again, we will meet in the next webinar. Thank you, sir. Thank you so much.
Thank you, sir.